So now that we've looked at calculating the pH of acidic solutions, let's now turn our attention to calculating the pH of basic solutions. And just like before with our strong acids, we have strong bases such as sodium hydroxide, lithium hydroxide, potassium hydroxide, barium hydroxide. They dissociate 100%, meaning if we have 0.1 molar sodium hydroxide, since it dissociates 100% in water, that gives us 0.1 molar hydroxide. So 0.1 molar sodium hydroxide means our concentration of hydroxide is 1 times 10 to the minus first molar, 0.1 molar. The pH is 1. Therefore the the pOH is 1. Therefore the pH is 13 because the pH plus the pOH must equal 14. And strong bases, just like strong acids, means it's fairly easy, just really plugging in numbers on your calculator in order to get the answer to the pH of these solutions. Now, when we get to weak bases, it's another issue. Just like with weak acids, if you want to determine the pH of a weakly basic solution, you need to go to ice tables. And we have a dissociation constant for bases. Just like with acids, we had Ka. For bases, we have Kb. Now, the acid dissociation, recall, was Ha dissociates into H plus A minus. With Kb, we're usually going to write that in the Bronsted-Lowry format. Therefore, we're going to need to put in the water. And we don't have to worry because it's liquid. It will not occur in our equilibrium constant expressions, our Kb expression, but we need to include it in the equation. So if we have 0.1 molar ammonia, which is a weak base, it reacts with water to form the conjugate acid ammonium and the conjugate base hydroxide. So we see we have generated hydroxide in solution. So it is a Arrhenius base, and it's a Bronsted base also because it accepted a proton from the water. The Kb value that you would look up happens to be 1.8 times 10 to the minus 5. So what is the pH of this solution? Well, ice table, write our equation, ICE. We start with 0.1 molar ammonia. We're not going to worry about the water. It's a liquid, doesn't occur in our expression. No ammonium ion, no hydroxide, minus X plus X plus X. 0.1 minus X, X, and X. Here's our Kb equation, or the form right here. And plugging in the numbers, 1.8 times 10 to the minus 5th equals X squared over 0.1 minus X. Small number here times 10 to the minus 5th. So we ignore the minus X. We find that 1.8 times 10 to the minus 6 equals X squared. Square root it. 1.3 times 10 to the minus 3rd X equals X. And that's our concentration of hydroxide if we just plug in the little molarity right there. All right, so our concentration of hydroxide is 1.3 times 10 to the minus 3rd molar, which means the pOH is 2.88. The pH is 11.11. Remember, pOH is a negative log of the concentration of OH, and then subtract that to get the pH. Note, this number here has two significant figs. Our Kb has two significant figures, so our concentration of hydroxide has two significant figures. Therefore, the pOH and the pH must have two digits after the decimal. This pH of 11.11 is two significant figures. Because with pHs and pOHs, the significant figures are the number of digits after the decimal place. All right. So, as I said before, in general, with our weak bases, we're going to write that as A minus, the base. Since it's a proton acceptor, we need something to accept the proton. A minus plus water goes to HA plus OH minus. All right. Now, an interesting thing, if we look at the Ka versus Kb for a weak acid, and its conjugate base. For example, here's a weak acid, acetic acid. Here is its conjugate base, acetate ion. We know Ka, acetic acid, will dissociate into acetate ion plus H+. There's Ka. There's a Ka expression. If we look at this weak base acetate, this acetate weak base plus water is in equilibrium with acetic acid and hydroxide, which means if you put acetic acid into water, it releases H plus, the water turns acidic. If you put acetate ion into water, it releases OH minus. So it is basic. That's why acetate is a weak base. But if you look at these two reactions, you see, well, here's our Ka reaction, here's our Kb reaction. We've got some similar things happening here. Here's the expression for Kb. If you take Ka times Kb, so here's the expression for Ka that we had up here. Here's the expression for Kb that we have here. Ka times Kb, you see a lot of stuff cancels, and we're left with the concentration of H plus times the concentration of OH minus. Those are the only two things that did not cancel when you take Ka times Kb. Well, that's the expression for Kw. So Ka times Kb equals Kw, and we know the value of Kw, 1.0 times 10 to the minus 14th, which means if you were given the Ka of acetic acid, then you can calculate the Kb of acetate, its conjugate base, using this formula. So some books will not have Kb tables, they'll only have tables of Ka values for the acid, because from those Ka values in this equation here, you can calculate the Kb values. All right. Moving on. Let's look at the acid-base properties of ions and the acid-base properties of salts, ionic compounds. All right, just a few general notes. Anions tend to form neutral or basic solutions. We're going to look at that in a bit. Cations tend to form neutral or acidic solutions. So if you have just an anion, it tends to be basic, could be neutral. Cations tend to be acidic or could be neutral. And how do you know if an anion or a cation is basic or neutral or acidic? By really 4 rules. The first 2 we're going to discuss right now. The next 2 we will discuss on the next page. The conjugate base of a weak acid is itself a weak base. The conjugate base of a weak acid is a weak base. The conjugate base of a strong acid is pH neutral. So if we have HCl, that's a strong acid. The conjugate base of HCl is the chloride anion. Since the chloride anion is the conjugate base of a strong acid here, make sure I said strong, it's a strong acid, the conjugate base of a strong acid, chloride is neutral. Now, right now you're saying, oh, well, this chloride came from HCl, therefore it's neutral when it comes from HCl. But what if you had sodium chloride, NaCl? Well, that chloride ion would still be neutral because even though it came from sodium chloride, if this chloride ion were involved in an acid, it would have been HCl, and that's a strong acid. So chloride ion is always neutral in solution because if you turned it into an acid, HCl, it would be a strong acid. And so chloride is a conjugate base of the strong acid HCl, therefore it is neutral in solution. HCN is a weak acid, therefore anytime you see cyanide ion in solution, you know it is a weak base because the base, the definition of a base, Bronsted definition is a proton acceptor. If this accepted a proton, it would be HCN, which is a weak acid, and the conjugate base of a weak acid is a weak base. All right, and so here we can see there are equations where if we look at HCN, which has a Ka value of 4.9 times 10 to the minus 10, HCN plus H2O goes to H3O plus Cn minus. Just the dissociation of HCN in aqueous solution. Normal dissociation here. Here's the Ka. Note it's a very, very small value for that Ka. Well, what would be the Kb for Cn minus reacting with water? Cn minus plus water goes to HCN plus OH minus. Note this is a weak base because when it reacts with water, it produces hydroxide. All right. Well, recall Ka equals Kb times Kw. So to find this Kb, we just take the Ka times our whatever Kb is going to be, our x value here, equals 1 times 10 to the minus 14th Kw. Kb is 2.0 times 10 to the minus 5. That will be the Kb for this reaction here. And let's clear up something that might be gnawing at your brains here. We said that Cn minus is a weak base because it created OH minus in water. And some people might say, but wait, didn't it also make the acid HCN in water also? That is true. So then you're saying, well, shouldn't we count this acid? Isn't that going to affect the base that it produced? And the answer is no, because remember, a solution is basic if it produces OH minus in water. It's acidic if it produces H plus or H3O plus in water. So the acidity of solution isn't due to HCN. The acidity of solution is due to H3O plus when that HCN reacts with the water. So acidity is measured as the concentration of H3O plus, not the concentration of HCN. So yes, Cn minus plus H2O did produce HCN, which is classified as an acid, but it did not produce H3O plus. This reaction did not produce H3O plus, and it's the amount of H3O plus that determines how acidic something is. So when you see this reaction and you see, oh, this produced an acid, oh no, what do we do with that? The answer is nothing, because in this form there's no H plus released. So only OH minus affects the pH here. Okay. So question then, what is the pH of 0.1 molar NaCN? A little foreshadowing here. We're going to find out on the next page that Na plus is neutral. So what is a pH of 0.1 molar NaCN? We're really looking at cyanide ion here, and it's an anion. So we know that cyanide is an anion. It is the conjugate base of a weak acid, HCN. Therefore, it's a weak base. So we're going to have it react as a base. Cn minus plus H2O liquid in equilibrium with HCN plus OH minus. Ice table, ICE, 0.1. 0, 0, minus 1 plus 1 plus 1, 0.1 minus x, or excuse me, minus x plus x plus x, 0.1 minus x, x and x. Here's our Kb expression for this reaction here, our base dissociation. Plugging in our values for our Kb, x squared, can we get rid of this minus x? Yes, we can. So we work it through. Concentration of OH minus is 1.4 times 10 to the minus third. POH is 2.85, pH is 11.15. It is basic. Okay, so that's looking at the acid-base property of ion salts when you're looking at the cation. Or excuse me, when you're looking, the base is the anion. So let's recap this, because in our next video we're going to start by looking at the conjugate acids. So let's recap this. The conjugate base of a weak acid is a weak base. The conjugate base of a strong acid is pH neutral. Now let's look at the conjugate acids of various bases in the next video.